Alright, today I'm going to be tearing down this high voltage power supply. This power supply is made by Spellman High Voltage Electronics Corporation. It has a output of 5,000 volts at 800 milliamps with an input of 180 to 264 volts at 25 amps. We see the part number and the model number. We have the input terminals here. It's just a single phase input. 240 volts would normally go in there. On the other side, we have the interface connection, and we have a filament and sense connection, which would suggest that this would be used in conjunction with a large vacuum tube, probably a large triode vacuum tube and a radio frequency generator. This is the high voltage output, just standard BNC connector with a extra deep insulated center pin through the front ventilation hole. Through the front ventilation opening, we can see a large high voltage transformer inside, maybe a few film capacitors are in there as well. Not much else to see on the outside. If you happen to pick up one of these, don't bother asking them about the pinout to this interface because they just won't tell you. I know because I've tried. So I'll just get the cover off of this and we'll have a look. Okay, I got all the screws removed. So pull the cover off. There we go. Interesting. So on the top, it looks like we got the main control board. This looks like the filament supply section. A couple large choke inductors here. A little transformer there. A couple gate drive transformers. On the top here we have just looks like analog circuitry. Couple PWM controllers. Over here we have the main input filters, a couple fuses, large film capacitors, large common mode chokes. Up here this is a large contact relay. That's rated for 30 amps. There's a small cooling fan on the top here. On the side, we have quite a massive ferrite core high frequency transformer in here. That would be for the main high voltage. We have another large choke or transformer or inductor. 5 large DC bus capacitors. On the side, over here we have the main drive for the power semiconductors. It's cable here that interfaces from the top board down to the side, down to the main drive PCB, I'll call it. Over here it looks like we have a high voltage bridge rectifier made from discrete diodes. And this side looks more like the mains input side. This chip here is a L4981AD. I think that's a power factory control chip. I can see at least 8 power semiconductors. Actually, it looks like we have about 6 power semiconductors and 2 diodes. There's a large 10 ohm resistor up here. It looks like it could be used for a soft start pre-charge circuit. I'm gonna go ahead and pull these boards out so we can have a better detailed look at them. All right, here's the power supply with the top PCB removed so we can have a better look inside. We can see the large high frequency transformer over here. These two connections are the AC input after the common mode choke and filter and input protection. They go down to this large inductor. It's wrapped in very fine wire. It's actually wrapped in Litz wire around an iron core of very, very thin laminations. That mains input comes out of the common mode choke inductor, and one end goes to the pre-charge circuit through that resistor, which is bypassed eventually by the relay. And the other end of the AC input comes to a set of 4 large MOSFETs. These are IXFR 24N50Qs. These are 500 volt N-channel MOSFETs, which is pretty interesting. These are driven by a power factor correction chip. It looks like they have their gates commoned up on the top and bottom pair of transistors. The AC input goes to both the drains on these transistors. So I believe that's acting something like a synchronous rectifier of some sort. But then it also has these 2 diodes over here. Not too familiar with the circuit. That DC output comes out here and it goes up to these main DC bus capacitors. This connection comes out of the DC bus, and this provides a voltage supply for the filament inverter. So that main DC bus comes over to a pair of IGBT transistors. These are APT50, GP60, B2DQ2G. They are 600 volt, 150 amp IGBTs. There are actually only 34 left in DigiKey stock, and about $14 each. And that forms a half bridge between 2 large film capacitors that we can see on the inside. Just down there, those 2 big white film capacitors. And that is used to drive the high frequency transformer to get our high voltage output. I'll pull the rest of this board out so we can get a better look at it. All right, I got the main power components all separated from the case. And I just want to get this heatsink off, and it's kind of stuck. So I'm just gonna go in here with this. There we go. Heatsink released, and it has a little temperature switch on it. Nice heatsink. Now we can see the back side of the main drive PCB. And so to get a better look at this, I think I want to go ahead and unsolder these large connections. I don't think my little soldering iron is going to be good enough to get these off. So I'll go ahead and grab my jumbo-sized soldering iron to get these large connections off. Okay, I got my humongous 300-watt soldering iron that I built myself. I'm going to turn it on. We're going to let it heat up. The way I built this is I took a piece of brass and I drilled a hole down the center and inserted a cartridge heater. It's a 300-watt cartridge heater. It has a thermocouple inserted into the tip, and that runs down to a PID temperature controller and a solid state relay to control the cartridge heater. The tip is tin plated, and it's very useful for undoing large connections. I made it originally because I had intentions of building my own large EV battery for an electric bike that, of course, I never got around to doing. So it's useful for other things, like unsoldering large lead-free solder connections. So once this heats up, this will heat up to about 700 degrees. We can start unsoldering these connections. And I am running out of 60/40 solder, which is never a good thing. As you can tell, it heats up quite fast. So I'll just give it a minute to heat up. All right, my soldering iron is fully heated up. Just like that. There's another one down here. Just like that. Go ahead and try to grab this large cable here. Nice and easy, comes right out. Next one here. Boom, easy. It's a large transformer removed. More solder on my tip here. Hopefully you can see this. Boom. Not a problem. Ow, it was hot. Okay. And the last one here. Need to get some fresh solder on there. Let me get you a little closer so you can see this in detail. Easy. So here's the main power drive circuit board that is used to drive the high frequency transformer. It uses a half bridge topology. Here's our two IGBTs for the half bridge, the two large capacitors, 400 volt, 20 microfarad. This is actually not a gate drive transformer. What this is used for is that they're creating a isolated power supply for the gate drive. So down here is a UC352580W, that's a PWM controller, and that's driving these two transistors. That drives this transformer. That transformer has two separate windings, and they come up here to the gate drive circuit. That transformer comes up to a full bridge rectifier, and that it provides a power supply to this isolated gate drive chip. That gate drive signal eventually comes from the main circuit board. That's traced up to this connector. It goes up to the main PCB. So that's just a way of creating an isolated gate drive. Up here, we have a small power supply, 24-volt power supply for the rest of the circuit that would drive the cooling fans. Over here, we have a high voltage full wave rectifier built with discrete diodes. There you can see the part number. These are BEW12S. I have some surface mount resistors to act as the voltage divider. I've got a couple of current sense resistors here. Some nice ceramic capacitors on the DC bus connected close to the IGBT transistors. This is a current sense transformer for the half bridge. These are two current sense transistors or current sense transformers for the mains input side. Got a couple of high voltage film capacitors over here. And that's basically it. Not much else to see on here. Here's that mains AC filter inductor or filter choke or common mode choke. It's actually wound with very thick Litz wire. I have a sample of that Litz wire here. It's about a 10 gauge wire or 8 gauge wire, it looks like. And the diameter of that Litz wire is about 140 thou. Here is the main high voltage transformer. It has a single layer winding on this end. And then, interestingly, the winding comes out and is wound in the same direction around the secondary side in a single layer. Here is the output from that high voltage. Nice thick ferrite transformer. Transformer is approximately 1 inch, 25 millimeters by 4 inch or 102 millimeters. Here's a cooling fan. Nothing special here. 24-volt cooling fan. Interesting detail on this cooling fan is that it has multiple positions for adding balance weights. This is one PWM controller. It's a UC3825ADW, and this is used to drive the half bridge. This chip here, A3700, that's a AC voltage detection chip that tells the rest of the circuit that there is sufficient AC input voltage. Over here we have another UC3825ADW, and that drives these two gate drive transformers. This is used for the filament supply. This is the connection that comes from the main DC bus capacitors. It goes through a common mode choke. Some large surface mount capacitors. There's a couple of transistors here, or MOSFETs. These are 89NK60ZDs. Here is a better look at those. Those are used to drive this small high frequency transformer. These gate drive transformers also drive these pair of MOSFETs or transistors that's used to rectify the output of the filament transformer so that we can drive the filament with DC current. And once again, our filament connection. And around the board here, nothing special, just op amps, various types. A few test points here. And well, that's about it, honestly.